One thing you're going to see a lot. One thing you're going to see a lot are the words that I've highlighted. Okay, that's the reason I've highlighted them. They're not highlighted on yours, but they are underlined and kind of arrows with it because you're going to see that these words are used quite a bit. These words right here are key, are kind of the red flag that hey, this is exponential growth and decay. Because on the AP test, you might see a few questions like this, but you won't know how to do it unless you know this is an exponential growth and exponential decay problem. So how do you tell? Well, these words right here in front of you. Okay? Most likely they won't have all of the words, but they'll have some part of that. Okay? Usually it's this part here. Is directly proportional. Once you see that, you know it's exponential growth and exponential decay. All the problems we have today will have that. They will have that. But when you're looking at a test of 40 problems, that's what you're looking for. Okay? So today they're all out. But like I said, when you're on taking a test and there's 10 questions or 40 questions on the AP test, how do you know this is exponential growth and decay? Well, the little things. Most likely they'll have something like that. Is directly proportional. Okay? So this is what we're going to use. The rate of change. So anytime we have a rate of change, that's a derivative. That's where that comes from. The rate of change in y. So when we're finding derivative of y, we use dy over dx. Is, in math, is means equals. Right? Directly proportional. Directly proportional refers to this guy here, k. Okay? K is a constant of proportionality. That's what it's called. Okay? To y. And then this guy is just plain y. Whatever the dependent variable is, that's what it is there. Okay? So this is what we're going to use for every single problem today. All right? Okay, so let's look at the first one here. First one here is the same exact thing, right? But they want you to solve it using separable differential equations. Okay, so what I want you to do is solve it just like we've been doing. Just like we've been doing, solve it. Okay? I'll give you a few minutes to do that. See what you get. Okay? K is a constant. It's a constant of proportionality. Constants. We don't worry about constants. It's not a letter. It's not a variable, I should say. It's not an independent variable. Okay? So by now you guys should know how to do this really, really, really well because we've been doing it a while. This is the one thing we've done every single section of this chapter. dy equals k times y times dx. Divide by y. One over y dy equals k dx. Right? Integrate, just like we did. Been doing. Integrate both sides. Okay. This side over here, k is a number. It's not a variable. It's a constant. So the derivative or the antiderivative of k would just be kx plus c. 1 over y is just the natural log of y. The natural log of y. Okay. Step 3, plug in points. Well, we don't have points for this problem. They didn't give us points, so we skip that step. Step 4, solve for y. Well, to solve for y, how do we solve for y here? Yeah, we're going to have to convert it to exponential because there's no way to get rid of the log. I have to separate. In order for me to solve for y, I have to separate these two guys. And I can't unless I convert it to exponential. So we're going to be doing this a lot today too. The base here is e. So we've talked about this before, and you went over it in Math 3, but you're gonna need to be really, really good at this today. To convert it, right? We start with the base, move here, that becomes the power, that becomes what it's equal to. Okay, so it's going to be e to the kx equals y. Okay, because we're going to be doing that a lot. We're going to be moving from exponent form to log form and log form to exponent form, going back and forth, back and forth, back and forth, especially today. Anytime you deal with exponential stuff, exponential growth, decay, that's what you're going to be doing. Okay. Okay, so that's where we stopped in past notes. Today, we're going to continue on with this. This is going to be part of what we use to help solve today's problems. Okay, but what I'm going to do is a little something different here. Using rules of exponents. How can I break this up? How can I break this guy up into two parts using rule of exponents? Yeah. There you go. Right? It's kind of undoing it, right? Rules of exponents say when you have the same base, you add their exponents. That's what I did. I just undid that. Okay? The reason I did that, there's an important reason I did that. The reason I did that is because e to the c, what is e? Not like what is e, but in practical terms, what is e? E's a number, right? E's just a number. It's not a variable. E is not a variable. It's like pi. Pi's not a variable. Pi is a number, right? You got that note, you got that button on your calculator. You got the E button on your calculator, right? And C, what is C? A number. It's a constant, right? So really, e to the c is not a variable, right? Is not a variable. Over here, I have a variable, x, right? X is a variable. But e to the c is not a variable. It's a number, right? It's a constant. So what I do here is I'm going to label a little differently. So this is a constant. Okay. So I'm going to give this a value. I'm going to call this, instead of e to the c, I'm going to call it a. Today we're going to call it a. So we're going to say a times e to the kx. Okay, that's what we're going to call it today. We're going to be using this guy a lot. Okay, this is the guy we're going to be using on every problem we do in this. I think every problem, definitely today. Every problem we use in to solve the problem, we're going to be using this guy a lot. Okay. Okay, so let's go to an actual problem. Okay, so bacteria in a culture increased from 400 to 600 in 3 hours. So in 3 hours, it increased in population from 400 to 600. Assuming that the rate of increase of the population is directly proportional to the population, they want us to do a couple things. Okay, so in that first two sentences, how do I know that this is going to be exponential growth and exponential decay? How do I know? There you go. Right there. Those words that we were looking for since the first page. Right there. That tells us we're doing exponential growth, exponential decay. Now this one looks like growth because it's growing, right? The culture is increasing from 4 to 16, okay? So it's in exponential growth, all right? So that tells you, that's the key in your head. Okay, we're gonna use what we use today, all right? Okay, so first thing we gotta do is come up with an equation to model this population. Because the second question they're gonna tell us is, okay, so how many are there at the end of 6 hours? At the end of 6 hours, how many are there gonna be? To solve that question, we need an equation, okay? So what we're going to do is we're going to use our equation. We're going to start with our equation right here, this guy right here. Except we're not going to use y's and x's. We're going to make it fit what we're doing, right? So instead of dy over dx, instead of x's and y's, what would be better to use on this problem here? Instead of using x and y, what would be more fitting for the independent and dependent variable? Instead of using x and y, because sometimes x and y, you're like, which one was x and which one's y? They don't mean anything, right? They're just general terms. Well, instead of using x and y, we can use other letters, right? So what other letters would be more helpful in this problem? What is x and what is y? Yeah, you read? So one of them is population, right? And one of them is time, right? Hours in this case, but time, right? Definitely. Which one is x and which one is y? Is population going to be x or time going to be y? Or vice versa?
Population would be X, or population would be Y.
And which one would be x?
The hours.
Good, good, yeah. Yeah, here's a general rule. Time is 99.9% of the time, if you have time, it's going to be your x, right? Because time we can't control. Time's always independent. Time does what it wants. We can't control time, right? Everything is based off of time. So it's been this way forever. And if you guys see it and you're like, which one's x, which one's y? Time is usually always going to be the independent variable because we can't control it. It's independent. Okay, good. All right, so we're going to rewrite this. So don't write this part yet. Don't write this part. So instead of y, what did we say we're going to choose? Instead of using y, we're going to say population, okay? So instead of y, I'm going to use a capital P for population. And then what did we say for x? We're going to use, instead of x, we're going to use time. Okay, that's what I want you to write. That's what I want you to write. Now, is it wrong if you use x and y? No, it's not wrong if you use x and y. But having taught this before many, many times, it's always easier if you change the letters to mean something. So that when you get at the end, you say P equals, you know what it means. The population of after 6 hours is that, right? If you just have y, then you have to do some extra thinking and be like, what was y again? Was it, what was it? Right? So it just helps. Okay. Okay, so that's the first step. Now, what did we do the last time on the last problem with something similar to this? The last problem, just the last problem we did 2 minutes ago. There you go, solve it again. Solve it for, let's see, so we're gonna solve it for t in this case. We're gonna solve it for t. Okay, so do that right now. So we want the independent on the right, dependent on the left. So we don't have x and y's. So independent means the x's, dependent means the y's. So t is the independent, so that's going to be to the right. Anything with a p is the dependent, the old y is going to be to the left. Okay. Then we do the same thing we did on the last one. We separate and integrate. So we're going to get the natural log of p here. And then we're going to get k what? It was kx before. It's not going to be kx this time. What is it going to be this time? kt, because t is the independent variable now. Okay. Okay, so let's see. E to the kt plus c equals p. P is our independent our dependent, right? So p, we're solving for p instead of y. And then what did we do after that? What did we do with that guy when we solved this? We had different letters, but what did we do? Exactly. E to the k, oops. Right? And then we said, hey, this guy right here is a constant. So we gave it the letter A. Okay. All right. That guy should look familiar. Instead of P's and T's, we use X's and Y's, right? But it's the same formula. Okay, we're going to use it. That's not our equation, though, because we don't know what A is. How many variables do I have in this equation here? How many variables do I have in this equation here? One, none, a million. How many do I have? Two, yeah. Which two are they? P and T, right? P and T. K is a number too. K technically is a variable right now because I don't know what it is, right? It's a constant, right? It's like E, it's a constant. I just don't know what it is. So for that matter, K is one too, right? So K, T, and P. Well, it's not an equation if I don't know what three of the letters are. So I have to figure it out. So how do I figure it out? The next step is use what you know. Use what you know. So let's go back up here. Okay. So I have P equals AE to the KT power. Okay. So what I know is they've given me a couple things to start out with. They said, hey, the bacteria in the culture increased from 400 to 1600 after 3 hours. Okay. So 400 is the population. 1600 is another population. What time goes with those? What time goes with 400? What time goes with 1600? Mm-hmm. Yeah, we can use 0 as 4. How can we use those to make an equation? Because once I have an equation, right? Because I know down here, letter B, to answer that question, T is going to be 6. All right? 6 hours. T is 6. That's not hard. Plug in 6. But what happens if I plug in 6 to this equation here? What would happen then? I have a P, I have an A, I have a K. That's not a number, right? I need a number. So that's not going to help me, right? So T is the only variable I want left. So what do I have to solve for before that? So what can I do? What can I do? Critical thinking, critical thinking. Plug in, yeah, plug in. What can I plug in? Let's try 0 and 400. Okay. So what do I plug in for 0? Where do I plug in 0? And where do I plug in 400? Okay, let's do it. Do it. Do it. Pencils, right? Let's go. Don't wait for Mr. Flores to give me the answer. Okay. So when I simplify this, I get 400 equals a e to the what power? 0 power. Well, that's helpful. What is e to the 0 power? 400, right? Or sorry, 1. So what does a equal? Boom. Now I know what a is, right? So let me change this guy here. $400. Now I know 400 goes there. Almost there. What else do I need to solve B? Because the reason I'm doing all of this is to solve B. I need to solve B. So when I plug in 16, I want to get a number for P. I got my calculator ready to go. My calculator is ready to go. But if I plug in numbers, if I plug in 400 times e to the kt, and I plug in 6 for t, what's going to happen? It's going to say error because I don't have enough information. So what information do I need? Still, find k. If I had k, then my calculator will calculate an answer, right? 400, e is just e. I got a button like that on my calculator. I'm okay there. T is going to be 6 down here, right? But I don't know what k is. So I got to figure out what k is. So let me use my extra point. I got an extra point, right? 316. Plug in 3, plug in 1600. When you plug in 3, when you plug in 1600, you get a number. All that's left is E and K. I'm not worried about E. E, I have that button on my calculator. I know what that is. Now I can solve for K. Okay, so we have 1600 equals 400 e to the 3k. How do I solve for k? What do I do first? Yeah, I would do, first thing I would do is good, divide by 400. Good, multiplication, so you can do that. Okay, so you get, let's see, that's 4 equals e to the 3k, good. That helped a lot because now the big numbers went away. Where's my guy I want to solve? Up here. How do I get him down to the ground? How do you solve equations? This is how do we, when we need to solve equations that are up in the air, the variables up in the air, how do we bring it down to the ground? Because I can't solve it if it's up in the air. Mhm. Exactly. That means if it's like that, that means I need to bring it down to the ground. That means log, right? So I told you guys at the beginning of today, you're gonna have to be your skills to move back and forth, back and forth. If you remember, it's like this. If I have the natural log, because we're going to be dealing mainly with natural log. So you have the natural log of x equals y. To change it, you're going to have e to the y equals x to go back and forth. That's just math 3 stuff. That's not math 1. That's not calculus stuff. But you're going to need to be able to go back and forth, back and forth, back and forth. We've already had one where we needed to go this way, where we needed to go from this way. But now we need to go the opposite way. So what would that look like? What would that look like? There you go. Natural log of 3k. Oh, sorry, the other way around. Sorry, yep. The natural log of 4 equals 3k. Because you have e here, that's the power, that's the answer. E power answer. Okay. Anytime I'm trying to change it, that's what I use. I just say, start with the base, and then that's the power, or that's the base still. That's the power, that's the answer. Okay. Well, this A is not a calculator question, so I'm not gonna answer natural log of 4. I'm not gonna get a decimal for natural log of 4 yet. When I get to B, I will. Okay. Solve for 3 or solve for k. Divide by 3. Divide by 3. Or instead of dividing by 3, I'm just gonna say 1/3. So k equals 1/3 natural log of 4. There's a reason why we're not gonna plug this into our calculator, and I'll tell you in a second why we're not. Okay, so our equation now, our finished equation, is P equals 400 e to the 1/3 natural log of 4 t. That's our equation. That's the equation we're going to use for, that's the answer's A, and we're going to use for B. Now, the reason you don't use the calculator until the very end is because let's say you rounded this answer here. Let's say you rounded this answer here and went to your calculator. And then you plugged in T. You're going to be extremely off for letter B if you do that too soon. I would not round. Don't round until the very end. If you can keep stuff as fractions, keep it as a fraction. If you can keep from going to a decimal, save it for the very end. Don't round until the very, very end. Because I've seen people round 1/3, round this guy. So they have 0.33 times that, and then they get to their finished answer for B and it's nowhere close. It's nowhere close. And they're like, I did everything right. And I'm like, yeah, I can give you credit for A, but you rounded too early. So B, you're way off. So don't round until the very end. Okay. Okay, so now let's plug in. Now we're going to use our calculator. Now we can use our calculator. P equals 400 E and then I'm going to plug in 6 here. Okay, so use your calculator. What do you get? You don't need a fancy calculator for this question. Regular Scientific calculators have natural log buttons and E buttons, so you don't need a fancy calculator for this guy. If you don't have a calculator, just use your phone. It's got all of those buttons. If it's a scientific calculator, it's got all those buttons. So if I'm plugging this in, here's another thing I see a lot. It's not a tip, it's just a mistake I see a lot. I see a lot of students wanting to take the easy way and they plug this whole thing in there at once. The problem with that is your calculator is really good at order of operations, like really good at order of operations. And if you put it in incorrectly, you might think it's correct, but if you put parentheses in the wrong spot, your calculator will, like right now, your calculator knows, how do I say this? Your calculator knows order of operations really well. So it might do things you don't want it to do first. Like it might multiply things that you're like, whoa, I don't want you to multiply that first. I want this. So students, I get this all the time. They put this whole thing in there and then they get an answer that's way off. And I'm like, no, that's way off. Like, but I put it in there. I'm like, well, you missed parentheses or something. So this is what I would recommend. I would recommend doing the power first. Get a number for the power. Go natural log of 4 times 6 times 1/3. And then take e to that power and then multiply by 400. Okay? Because even if you have a fancy dancy calculator and try to do all of that at one swift move because you think it's going to save time, it really doesn't just save you time. It really doesn't. Go one step at a time. So let me get my calculator out and show you. So we know what, this is another way to know if you're right? We already know the table. We already have values on the table, and the question is asking for 6, right? The question is asking for 6. So you kind of have an idea of what it should be, right? You kind of have an idea of what the answer should be. So if you're getting an answer that's nowhere near that, then you know you did something wrong, right? So for this guy here, yeah, I don't even want to do it that way because it's going to waste time. So 1/3, so I go 1/3, 1 divided by 3, and then I go parentheses, natural log of 4, close parentheses, and then I do times 6. That's my power, okay? And then I go e to that power. My e button's right here, to that power. And then I go times the last one, which is 400, and I get 6,400. 6,400. Well, let's go up here. The 6,400 mesh with what I already have. The 6,400 kind of makes sense in context of what I already have. 0, 400, 3, 1,600, 6, 6,400. Does that make sense? Yeah, it does. Okay. This one was nice and neat problem, 6,400. This is the only problem you're going to have where it's nice and neat. Okay. I started out with that one first, so it would give you nice and neat. They will not give you nice and neat problems. Okay, so don't expect that kind of nice and neat. If you get a nice and neat answer, great, but don't expect that all the time. Okay. Okay, so let's look at number 2. We're not going to have time to finish number 2, but what I want you to do is underline, highlight, circle, anything that's important. You know what you're going to be using. Read the problem, underline, highlight, make a table if you can. What is the stuff we're going to be using? Okay? That's if we can get that done for today, that would be great. So tomorrow we can just jump right into the problem. We're going to have a formula, an equation, and then we're going to have to find when t equals 1,000. Is directly proportional. That means we're going to use the same steps we've been using. Okay? What is the independent? What is the dependent? Let's start with that. Yes, for years, definitely T. What about P, or sorry, the top? What do we have here? They say radium-226, which is an element, right? They don't really say that comes in M, I guess, for mass we could use, or R we could use for radium, the amount of radium. Okay, so either one is okay, dr or dm, that's okay. So that's going to equal Kr. Well, when I separate and solve that guy, what do you think I'm going to get? You can do it, but we've been getting the same things over and over and over again when we separate and solve. What do you think we're going to get when we have this guy? What do you think we're going to get when we separate and solve? Or if you don't know, separate and solve it. Actually separate and solve it. Yeah, M equals or R equals. Say it again. Yep. That's what we would get. That's the place you always start if you're doing these problems. You always start with that. Okay. So now I have R or M, whatever you were using for radium mass, and T. Oops, the other way around. So they give us a couple of things. They say if its half-life is 1,590 years, and if we start with a sample with a mass of 100 milligrams. So start means initial, so that means initial time is 0, 100 milligrams. Now, how do half-lives work? Those of you that guys have taken chemistry or are taking chemistry, how do half-lives work? What is a half-life? Yeah.
After 1,590 years, it'll be 50.
Exactly. That's exactly what it means. It'll have half of its life after that. So exactly, just like Sebastian said, after 1,590 years, it'll retain half of its life. So 50. That's what half-lives are. So if it says it has a half-life of 6,000 years, that means in 6,000 years, half of it will be left. Okay? So theoretically, it'll never go away. Things that have half-lives never die. Because if you keep taking half, you'll always have something left. Okay? All right, so that's it. That's what we got here. Okay? Always start with a 0. If they give you the 0, start with that. Let's plug in 0. So we have R equals A. Oops, not R. We have 100 equals A e to the k, and then time is 0. Okay, so we got 100 equals A e to the 0 power, which means A equals 100. Okay, good to know. So it's R equals 100 e to the kt. So we need to know what k is. We need to know what k is. Because if I know what k is, I can plug in t and get r. So use the other point. The other one was 50 equals 1,590. Oops, nope, that doesn't go there. 100 e to the 1,590k power. Solve for k. Oh, I put an extra 0. Thank you. Yep, put too many zeros. Okay. Divide by 100. So I get 1/2 equals e to the 1,590k power. Last thing, how do I solve for k? So the natural log of what? Yep, natural log of 1/2 equals 1,590k. Divide by that. Don't change it to a decimal. Leave it like that. And that's where we'll stop. We'll pick up, so we have that's where we'll stop for today. Okay. So